Come back into the dark with me. A star in the winter sky grew dim, not over centuries but across one northern winter, dim enough that careful watchers could see it with the naked eye. Betelgeuse, the red shoulder of Orion, had veiled its own southern hemisphere with a cloud of cooling dust, and telescopes turned in unison to witness something no instrument had ever captured: a star's surface transforming week by week. Tonight, I want to show you the night a star covered its own face, and the 6 months in which we discovered that even the most familiar light in the winter sky had not finished telling us what it was. If this journey steadies you, leave a small light behind, a like, a subscription, so others can find their way here too. Now let the room go dark. Settle into the quiet. Let your breath slow. We're going to a place where a star pulled a veil across its own face, and humanity watched it happen in real time, week by week, something no generation before ours had ever seen. Betelgeuse marks the shoulder of Orion, a red-orange ember in the winter sky, one of the brightest stars visible from Earth. It pulses, brightens and dims on cycles measured in seasons and years, a rhythm woven into the oldest oral traditions. But in late 2019, something changed. I am the cartographer of the dark. I have been mapping these distant places for longer than can be remembered, and tonight you travel with me to a red shoulder in winter, to watch a star do something no human had ever seen before. You know Betelgeuse without knowing you know it. If you have ever looked up on a winter night and found the 3 stars that mark Orion's belt, you have already found the constellation. Look up and to the left from the belt, and there, marking the shoulder of the hunter, is a star that burns with a color unlike almost any other point in the night sky. Red-orange, warm, unmistakable. Betelgeuse. The name comes down to us from Arabic, twisted through centuries of translation, perhaps from a phrase meaning the hand of the giant or the armpit of the central one, depending on which scholar you ask. The star itself has been watched for longer than we have records. Aboriginal Australian oral traditions may incorporate observations of its variability, stories passed down across thousands of years, encoding the fact that this particular star does not hold steady. It does not hold steady because Betelgeuse is not like the Sun. It is a red supergiant, one of the largest stars close enough for us to study in detail, and it breathes. Its brightness rises and falls on 2 overlapping cycles, one roughly 400 days long, the other stretching across nearly 6 years. For most of human history, these changes were subtle, the kind of thing you might notice only if you watched the same patch of sky night after night, season after season, and kept careful notes. The star would brighten, then dim, then brighten again, a slow rhythm written into the fabric of its enormous convective envelope. Astronomers catalogued it as a semi-regular variable, assigned it the designation Alpha Orionis, and watched it with the patience that comes from knowing a star operates on timescales far longer than a human life. Then, in October of the year 2019, Betelgeuse began to dim in a way that was unusual even for a known variable. The change was gradual at first, easy to miss unless you were paying close attention. But by mid-February of 2020, the star had faded from its typical brightness to roughly 1/3 of what observers expected. It had dropped from an apparent magnitude near half a point to nearly 1.7, a shift large enough that careful observers around the world began to notice without instruments. If you had been watching Orion that winter, you would have seen it. The shoulder of the hunter looked dimmer, cooler, as though something inside the star had changed. The dimming was not catastrophic. Betelgeuse remained one of the brighter naked-eye stars throughout the event. It did not go dark, it did not flicker out. It simply faded, measurably enough, that the question became unavoidable. What was happening to a star that had been watched for thousands of years? And why now, in our lifetimes, was it showing us something new? Betelgeuse sits somewhere between roughly 500 and 700 light-years away, close enough to stage a spectacular show, too far to threaten us. At that distance, even a supergiant star is just a point of light to the naked eye. But Betelgeuse is large enough in the sky that the best ground-based telescopes can resolve it as a disk rather than a point, one of only a handful of stars where this is possible. And so, as the dimming continued, observatories around the world turned their instruments toward Orion, not in panic, but in attention. Something was happening to a star's surface, and humanity had the tools to watch. This is a star so large that, placed at the center of our solar system, its surface would engulf the inner planets out to roughly Jupiter's orbit, or perhaps farther, depending on the measure. Its mass is somewhere between 16 and 19 times that of the Sun, but it has swollen to a size roughly 700 to 900 times the Sun's radius. The surface temperature is only about 3600 degrees Kelvin, cool by stellar standards, far cooler than the Sun's nearly 5800 degrees. It glows red-orange because it is enormous. The same energy that a smaller, hotter star would concentrate into a smaller surface is spread across a vast expanse, lowering the temperature per square unit. Most of the light it emits is infrared, invisible to human eyes. Only about 13% comes out as visible light, but even that fraction is enough to make Betelgeuse one of the brightest stars in the night sky, pouring out tens of thousands to over 100,000 times the Sun's luminosity, depending on the measure and the moment. This is a star that has been burning for less than 10 million years, a brief span in cosmic terms, but long enough to have passed through the main sequence and entered the final chapter of its life. Massive stars like Betelgeuse evolve very quickly. They burn through their hydrogen in a few million years, then move on to helium, then carbon, then heavier elements, each stage shorter than the last, until the core runs out of fuel and collapses. When that happens, Betelgeuse will produce a core collapse supernova, the largest class of stellar explosion. But that event, by the best current estimates, lies tens of thousands to roughly 100,000 years in the future. The dimming of 2019 was not a sign of imminent death. It was something else. What the telescopes revealed was a star that had veiled its own face. Images from the Very Large Telescope in Chile showed the southern hemisphere of Betelgeuse had become dramatically darker, an order of magnitude fainter than it had been just months before. The change was not uniform. The northern half of the star looked much as it always had, but the south had dimmed, as though something had moved between us and the star's surface, blocking the light. The images showed a star whose appearance had changed on a timescale of weeks. No one had ever seen that before. Not in any star beyond the Sun. The star had dimmed before. It would dim again. But this time, humanity was watching with instruments capable of resolving the star's surface. And what those instruments revealed was a phenomenon that had never been observed in a normal, non-explosive star. Betelgeuse had ejected part of its own face. A mass of gas had been blasted outward from the southern hemisphere, carried by a shockwave that had propagated through the star's atmosphere months earlier. As the gas traveled outward, it cooled, and as it cooled, it condensed into dust. The dust formed a cloud, and the cloud moved between us and the star, blocking the light from the southern hemisphere. The star had pulled a veil across itself, not by design, but by the physics of convection and shock and cooling, processes that operate on scales so vast they dwarf anything we know on Earth. The red shoulder of winter had shown us something new. Not a catastrophe, not a death throw, but a star doing what stars do, on a scale and at a moment when we happened to be watching with the right tools. The veil would lift, the dust would disperse. The star would return to its normal range, and it did by April of 2020. But the fact of the observation remained. For the first time, a star beyond the Sun had shown us its surface changing in real time, week by week. as though the cosmos had decided to let us see behind the curtain, just this once. Betelgeuse burns on, a giant in the winter sky, unchanged by what we learned about it. The dimming was not the end of its story, only a chapter, one we happen to witness. The star will continue for tens of thousands of years more, pulsing, dimming, brightening, ejecting mass, until the moment when its core finally collapses and the light of the explosion reaches Earth. When that happens, our descendants will see a point of light in Orion bright enough to cast shadows at night, visible in daylight for weeks, a spectacle sustained for months. But that moment is not now, and it was not then. The dimming of 2019 was something quieter, something stranger. A star showed us its face, and we saw it change. Perhaps you are listening from a city where Orion still rises in winter, or from a place where the hunter walks upside down across the southern sky. If you feel like it, leave your city and your local time below. We are curious who is listening in the dark. The story of Betelgeuse's dimming might have remained a curiosity, another entry in the long catalogue of variable stars, had the star been positioned anywhere else or appeared any smaller in our sky. But Betelgeuse sits close enough that its disk spans roughly 42 milliarc seconds across the heavens, a measure so small it sounds like nothing until you understand what it permits. The star is large enough in our view that the best ground-based telescopes can resolve it not as a point of light, but as a disk, a surface, a place with geography. Only a handful of stars beyond our Sun allow this. Most remain mathematical points no matter how powerful the instrument, their surfaces forever hidden behind the tyranny of distance. Betelgeuse does not hide. In the months before and during the Great Dimming, the European Southern Observatory's Very Large Telescope in Chile turned its SPHERE instrument toward Orion. SPHERE, equipped with a specialized camera called ZIMPOL, captured direct optical images of Betelgeuse's surface in January of 2019, again in December of that year, and through the spring of 2020, as the star climbed back toward its familiar brightness. These were not artists' renderings or computer reconstructions. They were photographs of a star's face, the only star beyond our Sun whose surface has ever been image-changing in real time on a timescale measured in weeks. The January 2019 image showed Betelgeuse as it had been, a mottled disk of red and orange, brighter in some regions than others, the surface roiling with convective cells larger than the orbit of Mars. The December 2019 image showed something else. The southern hemisphere had become dramatically darker, an order of magnitude fainter than the baseline, as if someone had drawn a curtain across half the star's face. The change was not subtle. It did not require careful calibration to detect. It was visible, immediate, a transformation unfolding on human timescales. For once, astronomers were watching the appearance of a star change week by week, not across centuries or millennia, but across the span of a single winter. The images conveyed their strangeness without interpretation. You could see it. Other observatories joined the watch. NASA's Hubble Space Telescope turned its ultraviolet spectrographs toward Betelgeuse, probing the chromosphere for signs of outward-moving gas. The Atacama Large Millimeter Array in Chile, a field of radio dishes scattered across a high desert plateau, observed the star in sub-millimeter wavelengths, tracing the thermal signature of dust grains forming in the cooling ejector. The gravity instrument on the Very Large Telescope measured the surface in infrared, mapping temperature variations across the disk. The Stellar Robotic Telescope in the Canary Islands tracked radial velocities, watching for Doppler shifts that would reveal gas moving toward or away from Earth. A global network of observatories, each tuned to a different slice of the electromagnetic spectrum, mobilized to watch something unprecedented. Not because the star was dying, not because anyone believed the dimming heralded imminent explosion, but because the star was doing something no one had seen a star do before, and the opportunity to watch it unfold in real time would not come again in any living astronomer's career. Betelgeuse had been a known variable for as long as humans had kept careful records of the sky. Its brightness rose and fell on cycles of roughly 400 days, and again on a longer rhythm of approximately 2100 days. The dimming that began in October 2019 was different. It was deeper than the normal variation, faster in its descent, and it affected the star's light unevenly. Some wavelengths dimmed more than others. The star's color shifted, and when the sphere images arrived, they showed why. The southern hemisphere had darkened not because the entire star had cooled, but because something had come between us and that part of the surface. The images themselves were small, grainy, each one the product of hours of exposure time and layers of adaptive optics correction to strip away the blurring imposed by Earth's atmosphere. But they were enough. They showed a star with a face, and that face had changed. The brightness that had once been distributed more or less evenly across the disk was now concentrated in the northern half, while the southern regions had faded into dusky shadow. The star had not turned off, it had veiled itself. This was not a simulation, it was not a model run on a supercomputer to predict what a red supergiant might look like during a mass loss event. It was an observation, a photograph, a record of light that had traveled somewhere between 500 and 700 years across the galaxy to reach a mirror in the Atacama Desert, where it was focused, filtered, and captured as an image barely larger than a thumbnail. And in that image, for the first time, humanity could see a star other than the Sun undergoing a visible transformation on a timescale short enough to matter to a single human life. Red supergiants lose material constantly, shedding the outer layers of their atmospheres into space in a slow, steady wind. Betelgeuse sheds mass equivalent to the entire mass of Earth, roughly every 400 years, a rate that sounds catastrophic until you remember the star contains more than 16 times the mass of the Sun, and that this loss is simply the way such stars age. What was unique was the scale and the suddenness. The southern hemisphere had not merely dimmed. It had been obscured by a cloud of dust that had formed from gas ejected by the star itself, gas that had cooled as it climbed away from the surface and condensed into grains of solid material, each grain small enough to float on a breath, but collectively thick enough to block the light of a star. The sphere images captured this veil in the act of forming. The December 2019 image showed the dust already in place, a dark patch covering what appeared to be roughly a quarter to half of the star's visible southern face. The images from early 2020 showed the veil beginning to thin as the dust dispersed or drifted out of our line of sight. By April, the star had returned to its normal brightness range, the veil gone, the surface once again visible in full. No human had ever watched this happen before. No instrument had ever been capable of resolving the surface of a star beyond the Sun with enough clarity to see such a structure form and dissolve. The Great Dimming was not the first time a red supergiant had ejected a cloud of dust. It was the first time one had done so while humanity was watching with the right tools pointed in the right direction. The images were published in the journal Nature in June of 2021, more than a year after Betelgeuse had returned to normal. The paper's lead author described the significance plainly. For once, astronomers had seen the appearance of a star changing in real time on a scale of weeks. Not inferred from spectroscopy, not reconstructed from models. Seen. The star had shown its face, and the face had changed. It had pulled a shroud of its own making across the southern hemisphere, darkening that region by a factor of 10 or more, and then let the shroud drift away. The event had been dramatic enough to notice from hundreds of light-years away, with instruments no more sophisticated than a backyard telescope, and detailed enough to image with the most advanced optical systems on Earth. It was a coincidence of scale and timing and technology, a moment when the universe's behavior and humanity's ability to observe it briefly aligned. The dimming had not been a warning, it had been a revelation. Betelgeuse had taught astronomers that a red supergiant could eject a localized mass of material large enough to veil a substantial fraction of its own surface. That such an ejection could happen on timescales of months rather than millennia, and that the dust formed in such events could cool and condense quickly enough to be observed forming in real time. None of this had been predicted. The star had simply done it, and the telescopes had watched. The fact that it happened to Betelgeuse, a star bright enough and close enough and large enough in the sky to be resolved as more than a point, meant the event could be documented not as a statistic, but as an image. The star had a geography now. It had regions that could darken and brighten independently. It had weather, in a sense, storms of gas and dust that could rise from the surface and obscure the light beneath. It was no longer an abstraction. It was a place, and it had shown us something new about what such places can do. The images remain. They are small, grainy, false-colored, to highlight details the human eye could never perceive. But they are photographs of a star's surface changing. The first, and so far only such photographs ever taken, of a star beyond the sun. They are evidence that the universe still holds events, no textbook anticipated, phenomena that reveal themselves not across deep time but across the span of a season, fast enough for a single observer to watch from beginning to end. Betelgeuse dimmed, veiled itself, and brightened again. The star continues, unchanged by what we learned. But what we learned has changed. When Betelgeuse dimmed by more than half its brightness in the winter of early 2020, astronomers around the world began asking the same question. What could make a star change its face so quickly? The images from the Very Large Telescope showed something unambiguous. The southern hemisphere of the star had darkened dramatically, an order of magnitude fainter than it had been just months before. But images alone do not explain themselves. They show what happened, not why. Three competing ideas emerged, each fitting part of the data, each incomplete on its own. The first was the starspot hypothesis. Red supergiants are known to develop enormous cool patches on their surfaces, regions where convective cells the size of planetary orbits bring cooler material up from below. If a starspot large enough to cover a quarter of the star's visible disk had appeared on the southern hemisphere, it could have dimmed the light we receive. The star would still be radiating the same total energy, but the cooler patch would emit less visible light, shifting more of its output into the infrared. The idea was plausible. Betelgeuse is large enough in the sky that its surface can be resolved, and the images did show a darkened region. But the question remained. Had anyone ever observed a star spot this large, this dark, appearing this quickly? The second explanation centered on pulsation. Betelgeuse is a semi-regular variable, its brightness rising and falling on cycles of roughly 400 days and 2100 days. These cycles are driven by the star's atmosphere expanding and contracting, like a slow breath drawn over years. When a red supergiant expands, its surface cools. When it contracts, the surface warms. The dimming could have been the result of a particularly deep pulsation, a moment when the star's outer layers had swelled to their coolest extent. The timing was suggestive. Betelgeuse had been in a dimming phase of its longer cycle, and the great dimming coincided with that trend. But the question was whether pulsation alone could account for the magnitude of the change. Emily Levesque and Philip Massey measured Betelgeuse's spectrum on the 15th of February 2020, near the peak of the dimming. They found an effective temperature of 3600 degrees Kelvin, give or take 25 degrees. This was cooler than pre-dimming measurements, but only slightly. The temperature drop was real, but modest. When they calculated how much dimming that temperature change should produce, the numbers did not match. The observed dimming was roughly 3 times what the temperature drop alone could explain. Something else had to be at work. The pulsation hypothesis could not stand on its own. The third idea was dust. Not dust floating in the interstellar medium between us and the star, but dust created by the star itself. Red supergiants lose mass continuously, shedding their outer layers into space through a stellar wind. When gas ejected from the star cools sufficiently, it can condense into solid grains, tiny particles of silicate or carbon that scatter and absorb visible light. If Betelgeuse had ejected a large cloud of gas that then cooled and formed dust in our line of sight, that dust could act as a veil, blocking a significant fraction of the star's light, without changing the star's intrinsic brightness. The idea was not new. Circumstellar dust had been observed around other red supergiants. But the question was whether Betelgeuse had ejected enough material, and whether it had done so recently enough to explain the timing and the scale of the dimming. Each hypothesis had its advocates. Each fit part of the puzzle. The scientific literature in late 2019 and early 2020 reflects not confusion, but the careful process of testing ideas against evidence. Multiple explanations can fit parts of the data, and scientists methodically test each one in public. That competition is exactly how science works. The spectrophotometry from Levaque and Massey pointed away from temperature alone. The images from the Very Large Telescope showed the darkening concentrated in the southern hemisphere, not spread evenly across the disk. A simple pulsation would have dimmed the entire star uniformly. A star spot could explain the asymmetry, but the temperature measurements suggested the star's overall surface had not cooled enough to produce such a large, dark feature. The dust hypothesis began to gain ground, but it required a mechanism. Dust does not appear from nowhere. Something had to eject the gas, and something had to cool it. Andrea Dupree and her team turned to ultraviolet observations from the Hubble Space Telescope. They examined chromospheric lines, emissions from the hot, tenuous outer atmosphere of the star, and found signatures of outward-moving material. The magnesium doublet lines showed gas flowing away from the star, carrying energy and mass upward. This was the connecting link. Large convective cells in the photosphere had driven a mass ejection event. Gas had been lifted from the surface, carried outward through the extended atmosphere, and released into space. The timeline fit. The shock wave that triggered the ejection had propagated outward from January through March of 2019, months before the dimming began. The ejected gas had traveled through the star's outer layers over the next 11 months, cooling as it moved. By late 2019, the gas had cooled enough to condense into dust grains, and those grains had formed a cloud in the southern hemisphere, directly in our line of sight. The dust hypothesis was no longer a hypothesis. It was an explanation supported by multiple lines of evidence. The temperature measurements ruled out pulsation alone. The imaging showed asymmetry. The ultraviolet spectroscopy showed mass ejection. The infrared observations, which peer through dust more easily than visible light, showed that the star's total energy output had not changed. The star was still radiating the same luminosity. The dimming was an extinction effect, a veil drawn across part of the star's face, not a change in the star's intrinsic brightness. The debate had not been a failure to understand. It had been the process of understanding unfolding in real time. Scientists had proposed ideas, tested them against observations, and refined their models as new data arrived. The star spot hypothesis was not discarded entirely. Starspots may still play a role in the complex interplay of convection and mass loss on red supergiant surfaces. The pulsation hypothesis contributed context, but the dust hypothesis, grounded in the mass ejection event, emerged as the framework that best explained the full range of observations. The star had ejected a significant fraction of its annual mass loss rate in a single event. Estimates ranged from 3% to more than the entire year's worth of mass loss, depending on assumptions about the density and distribution of the ejected material. The ejection had been powerful enough to disrupt the star's normal behavior. Following the event, Betelgeuse's 400-day pulsation cycle disappeared for more than 2 years, replaced by an unusual shorter oscillation. The chromosphere was left with reduced density, as if the star had exhaled and not yet drawn its next breath. The competing theories had not been a sign of ignorance. They had been the necessary first step. Each idea had carved away part of the unknown, narrowing the space where the answer could hide. By the time the dust settled, both literally and figuratively, astronomers had witnessed something no human had seen before. A star had ejected part of its own surface, cooled that material into dust, and veiled itself from view. The process had unfolded over months, visible to anyone with a telescope, and to careful observers with nothing but their eyes. The theories had competed, and the evidence had chosen. In the early months of 2019, something began moving inside Betelgeuse that would not become visible to us for nearly a year. Deep within the star's photosphere, a shock wave formed and began to propagate outward. Not an explosion, not a collapse, but a pulse of energy, traveling through layers of superheated gas as wide as the orbit of Mars. The shock moved upward through the star's extended atmosphere, pushing material ahead of it, accelerating plasma outward into space. For months, this event remained invisible to human eyes, detectable only in the ultraviolet signatures of chromospheric lines captured by instruments aboard the Hubble Space Telescope. The star was ejecting part of itself, and we were watching the prologue unfold in wavelengths our eyes cannot see. By late 2019, the ejected gas had traveled far enough from the star's surface to cool. When gas that hot expands and cools, it does what smoke does in a chimney or vapor does in the high atmosphere. It condenses. The atoms that had been torn apart by heat began to find one another again, forming molecules, then grains, then particles of dust. This was not the cold dust of a comet or the silicate grit of a planetary disk. This was refractory dust, forged from the elements a red supergiant manufactures in its outer layers, and expels through its wind. Carbon, oxygen, perhaps silicates, cooling from thousands of degrees to hundreds, solidifying in the void just beyond the star's southern hemisphere. The dust cloud grew, grain by grain, a veil forming in space. By December 2019, that veil had thickened enough to block light. The southern hemisphere of Betelgeuse, as seen from Earth, dimmed by an order of magnitude in some regions. The dust was not covering the star the way a planet transits its sun. It was more like a curtain drawn across a quarter or perhaps half of the visible disk, obscuring the light that would otherwise have traveled unimpeded across 600 light-years to reach our telescopes. The star itself had not cooled significantly. Spectrophotometry taken in mid-February of 2020 measured an effective temperature only slightly below the star's normal range, around 3600 degrees Kelvin, far too small a drop to account for the dimming observed in visible light. The energy was still pouring out of Betelgeuse at the same prodigious rate it always had. Infrared observations confirmed that the star's total luminosity, the sum of all wavelengths, had not changed. Over 50 years of monitoring, Betelgeuse had remained steady in its total output. What had changed was how much of that light could reach us through the veil. This was the surface mass ejection, a phenomenon predicted in theory but never observed in a normal star, never watched as it unfolded week by week. Betelgeuse had launched a plume of its own atmosphere into space, not through a steady wind, but through a discrete, violent event. The mass involved was staggering. Estimates of the ejected material ranged from a few percent to more than the entire annual mass loss rate of the star, depending on how the cooling and condensation efficiency was modeled. If the higher estimates were correct, Betelgeuse had shed in one event what it would normally lose over the course of a year through its stellar wind. It had ejected a piece of its face. The dust cloud did not remain stationary. It continued to move outward, carried by the momentum of the original shock and the pressure of the star's radiation. By April 2020, the veil had dispersed or drifted far enough from our line of sight that Betelgeuse's brightness returned to its normal range. The southern hemisphere brightened again. The star, as seen through our telescopes, looked whole once more. But something inside Betelgeuse had changed. The 400-day pulsation cycle, the rhythm that had marked the star's variability for as long as astronomers had kept records, had vanished. In its place was a shorter, irregular oscillation, a photometric signal that did not match the star's known modes. The chromosphere, the layer of atmosphere just above the photosphere, was measured to have a reduced density. The ejection had not merely veiled the star. It had altered its structure, at least temporarily, leaving the outer layers in a state that would take years to settle. The causal chain, pieced together from observations across multiple wavelengths and instruments, formed a clear sequence. First, the photospheric shock in early 2019, propagating outward from the star's interior. Then, enhanced mass flow through the extended atmosphere over the following months, material traveling through regions larger than the orbit of Jupiter. Then, cooling and condensation in late 2019 as the ejected gas reached the right distance and temperature to form dust. Then, obscuration, the dimming we saw from Earth, as that dust blocked our view of the southern hemisphere. Finally, dispersal, as the dust continued its journey into interstellar space, leaving the star visible again by spring of 2020. Each step followed from the one before, a cascade of physics playing out on a scale so vast that light itself took minutes to cross the star's diameter. This was not a prelude to explosion. Surface mass ejections, the data suggested, are a normal feature of red supergiant evolution, part of the turbulent life of a star so large that convection cells on its surface can be wider than the Sun. The event was dramatic, unprecedented in its observation, but not a warning sign. The star had not begun its final collapse. It had simply done what massive stars do in their extended atmospheres, where the boundary between star and space is not a sharp edge, but a gradient, where gas and dust and magnetic fields tangle and erupt and flow outward in ways that no simulation had fully anticipated. Betelgeuse had taught us something new about how stars lose mass, how they interact with their own winds, how a shock can propagate through an atmosphere so diffuse that its outer layers blend into the void. The images from the Very Large Telescope's SPHERE instrument, taken in January and December of 2019, showed the transformation directly. In the earlier image, the star appeared roughly symmetric, a mottled disk, with bright and dark regions marking convective cells and temperature variations across its surface. In the later image, the southern hemisphere was dark, a shadow where light should have been. No other star beyond the Sun had ever been imaged this way, with enough resolution to see its surface change, to watch a feature appear and evolve and fade over the span of weeks. Betelgeuse is one of only a handful of stars large enough in angular size to be spatially resolved by ground-based telescopes. and it is the only one close enough and active enough to have shown us this kind of event. The timing was fortunate. The technology was ready. The star cooperated. The mass ejection left behind more than images. It left data, spectra, light curves, radial velocity measurements, all threading together into a narrative of how a red supergiant can erupt. The ultraviolet lines captured by Hubble showed outward-moving material in the chromosphere, the signature of gas being pushed away from the star. The sub-millimeter observations from ALMA tracked the dust as it formed and cooled. The optical photometry from robotic telescopes around the world documented the dimming and recovery in exquisite detail, night by night, a record of a star's brightness changing faster than its normal pulsation cycles could explain. The gravity instrument, using interferometry to probe the star's immediate environment, mapped the distribution of material around Betelgeuse, confirming that the dust was localized, not a uniform shell but a clump, a discrete cloud in the southern hemisphere. When the 400-day pulsation disappeared, it raised new questions. Pulsations in red supergiants are driven by the star's internal structure, by the way energy moves through its layers, and by the balance between gravity and radiation pressure. If the surface mass ejection had disrupted that pulsation, it meant the event had reached deep enough, or ejected enough mass, to alter the star's outer envelope in a way that affected its oscillations. The chromosphere's reduced density was another clue. The ejection had stripped away material, thinned the atmosphere, left the star in a state that would take time to rebuild. Over the months and years that followed, astronomers watched for signs of recovery, for the return of the familiar rhythm. By 2023, Betelgeuse had brightened to its highest recorded level in modern history, a visual magnitude of 0, suggesting that the pulsation had re-entrained, that the star had found its rhythm again. The veil had lifted, but what it revealed was not the star returning to normal. It was the star continuing, as it always had, through phases of brightness and dimness, expansion and contraction, mass loss and pulsation, all the turbulent processes that define a red supergiant's final 100,000 years. The surface mass ejection was an episode, a chapter, not an ending. The dust dispersed into space, adding to the material Betelgeuse sheds constantly through its wind, enriching the interstellar medium with the elements forged in its core and dredged up through convection to its surface. Carbon, oxygen, nitrogen, all the raw material for future stars and planets, now drifting outward in a cloud that will one day be indistinguishable from the rest of the galaxy's diffuse gas. What we learned was not that Betelgeuse is dying, but that it is alive in ways we had not fully understood. That a star can eject part of itself and recover. That the boundary between a star and its surroundings is not static but dynamic, shaped by shocks and winds and eruptions. That the universe still holds events we have never seen, waiting for the right moment and the right instruments to reveal themselves. The surface mass ejection was a gift, a window into stellar physics that opened for a few months and then closed, leaving behind data that will be studied for decades. Betelgeuse continues its slow burn, its outer layers convecting and pulsing, its core fusing helium into carbon and oxygen, its wind carrying away mass grain by grain, shock by shock, veil by veil, under the same stars that have watched it for millions of years, indifferent and patient and vast. The star you are looking at when you find the red shoulder of Orion is not a point. It is a volume so vast that if you could lift Betelgeuse from its place in the winter sky and set it down where our sun burns, its surface would stretch outward past Mercury, past Venus, past Earth, past Mars, and reach somewhere near the orbit of Jupiter, perhaps farther, depending on which measurement you trust. Betelgeuse lies somewhere between roughly 500 and 700 light-years away, close enough to stage a spectacular show, too far to threaten us. The distance is debated because the methods disagree. One team measures the star's pulsations and derives a distance near the shorter end of that range. Another analyzes its motion and brightness, and arrives at a figure closer to 700. The difference matters because distance sets the scale of everything else. A star farther away must be larger and more luminous to appear as bright as it does. So when astronomers say Betelgeuse is roughly 700 to 900 times the radius of the Sun, they are offering you not a single number, but a range that encompasses the honest limits of what we can measure from here. The mass at least holds steadier. Betelgeuse contains between 16 and 19 times the mass of our Sun, compressed now into a core no larger than Earth, but wrapped in an atmosphere that extends for hundreds of millions of miles. The star is less than 10 million years old. That may sound ancient by human measure, but for a star it is youth cut short. Massive stars live fast. They burn through their fuel at a pace that leaves no time for the slow aging our Sun will endure. Betelgeuse was born, grew enormous, and will die in a span shorter than the time it takes our Sun to complete a single lap around the galactic center. The surface temperature of Betelgeuse hovers near 3600 degrees Kelvin. For comparison, the Sun's surface reaches nearly 5800 degrees. Betelgeuse is cooler not because it produces less energy, but because it spreads that energy across so much more area. The same furnace, diluted across a surface area hundreds of thousands of times greater than the Sun's, yields a lower temperature per square meter. The star glows the color of coals, not because it is dying, but because it is vast. And yet the energy pouring from Betelgeuse dwarfs anything our Sun could muster. The star radiates somewhere between tens of thousands and more than 100,000 times the Sun's total luminosity, depending on which distance and brightness measurement you adopt. Only about 13% of that energy emerges as visible light. The rest flows outward as infrared, a heat you could not see but would feel if you drifted close enough, long before the visible glow became unbearable. Betelgeuse has served as the standard for its spectral class since 1943. When astronomers classify a star as M1 or M2 Ia-AB, they are measuring it against Betelgeuse. It is the reference, the template, the star, by which others of its kind are known. A red supergiant of intermediate luminosity, cool and enormous, burning helium in its core and shedding its outer layers into space at a pace that will, over time, strip away a significant fraction of the mass it was born with. The star does not sit still, it pulses. Its surface rises and falls in great slow waves, driven by instabilities deep within. For decades, astronomers tracked a rhythm of roughly 400 days, a cycle of brightening and dimming that repeated with the regularity of a heartbeat. A longer cycle, near 2100 days, wove through the shorter one, adding complexity to the pattern. These rhythms are the visible signature of the star's interior structure, the outer skin responding to pressures and flows originating far below, in regions no telescope can see. When the surface of Betelgeuse moves, it moves on a scale difficult to grasp. A convective cell on this star, a bubble of hot gas rising from below, can span a region larger than the orbit of Earth around the Sun. The entire visible disk of the star would show not a smooth sphere, but a mottled, churning surface, bright patches and dark patches shifting and merging as gas circulates through the outer layers. The star is not a static ball, it is a dynamic system, a fluid body held together by gravity and torn apart by its own energy, balanced between collapse and dispersal. Because Betelgeuse obtends an angle of roughly 42 milliarcseconds in the sky, it is one of only a handful of stars large enough and close enough to be spatially resolved by the best ground-based telescopes. Most stars remain points of light, their disks too small to image. Betelgeuse is different. You can photograph its surface, you can watch its spots and plumes. You can see it change, not over millennia but over weeks. That ability is what made the Great Dimming observable. When the southern hemisphere of Betelgeuse darkened in late 2019, astronomers did not merely measure a drop in total brightness. They saw the darkness spread across the star's face. They watched a shadow grow, they mapped it, timed it, and traced its evolution frame by frame. No other star beyond the Sun has ever been observed this way. The energy output of Betelgeuse, measured across all wavelengths over the 50 years before the dimming, showed no significant change. The star's total luminosity held steady. The dimming was not a failure of the furnace, it was a veil. Something had come between us and the light. Something that blocked the visible glow but allowed the infrared to pass. The star itself continued to burn as it always had. We simply could not see all of it for a time. Betelgeuse is often described as one of the largest and most luminous stars, close enough for us to study in detail. There are other red supergiants, stars like VY Canis Majoris and UY Scuti, that rival or exceed Betelgeuse in size. But those stars lie farther away, their surface is harder to resolve, their variability less accessible. Betelgeuse occupies a sweet spot. It is large, it is bright, it is close, and it is active. It is the star we can watch. The physics of a red supergiant is the physics of imbalance. The core burns helium into carbon and oxygen, releasing energy that pushes outward against the weight of the star's own mass. The outer layers, vast and tenuous, barely hold together. The surface gravity of Betelgeuse is so weak that gas can escape with relative ease, lifted by radiation pressure and the turbulence of convection. The star loses mass constantly, shedding material into space in a wind that carries away the equivalent of a small planet every few thousand years. This is not a catastrophe. It is the normal life of a supergiant, the slow unraveling that precedes the final collapse. When you imagine Betelgeuse, imagine a star so large that light takes more than an hour to cross from one edge of its photosphere to the other. Imagine a surface where the temperature varies by hundreds of degrees from one region to the next, where plumes of gas rise and fall over spans of time measured in months, where the boundary between star and space is not a sharp edge but a gradient. A slow fading from dense to tenuous, from bound to free. The star is a furnace, yes, but it is also a structure, a layered system with a core, a radiative zone, a convective envelope, a chromosphere, and a wind. Each layer has its own physics, its own timescale, its own role in the life of the star. The core burns in seconds. The convective cells turn over in months. The surface oscillates over years. The wind disperses over centuries. All of these processes overlap, interact, and feed back on one another, creating a system so complex that no single model can capture it fully. And yet the star endures. It has burned for millions of years. It will burn for tens of thousands more, perhaps longer, before the core exhausts its fuel and the collapse begins. For now, it is stable in the way a spinning top is stable, balanced not by stillness but by motion, by the constant interplay of forces that keep it from flying apart or falling in. Betelgeuse is not unique. It is one of many red supergiants scattered through the galaxy, but it is the one we can see. It is the one that dimmed while we were watching. It is the one that showed us for the first time what it looks like when a star ejects its own face. When the core of Betelgeuse collapses, it will produce what astronomers call a core collapse supernova, the largest class of stellar explosion. The star that veiled its own face in dust will, one day, tear itself apart from the inside out. What that moment will look like from Earth has been modeled, measured, and imagined, with the kind of precision that only comes from decades of watching other stars die in distant galaxies. The numbers are grounded now, no longer speculative, and they describe something both quieter and stranger than the phrase second sun might suggest. The most carefully constrained estimate comes from modeling work published in the months following the Great Dimming. At its peak, the supernova would shine roughly as bright as the half moon, about 9 times fainter than the full moon overhead on a clear night. That brightness would not spread across the sky like moonlight does. It would concentrate into a single point, a star that had always been a dot of red light in Orion's shoulder, suddenly blazing white and sharp enough to cast shadows on the ground. You would walk outside at midnight and see your own silhouette stretched across the pavement, drawn by a star more than 500 light-years away. The shadows would be crisp, the kind you see under streetlights, not the soft penumbra of the moon. That peak brightness would hold for more than 3 months. Night after night, the supernova would outshine everything in the sky except the moon and the sun, and perhaps Venus at its brightest. Then it would begin its long fade, but even in fading it would remain visible to the naked eye for weeks to months in full daylight. You could step outside at noon, shield your eyes from the sun, and see Betelgeuse burning in the blue. No telescope, no camera, just your eyes and a star that had decided to announce its death across the void. The color would shift as the explosion aged. Models suggest the initial flash, the moment the shockwave breaks through the surface of the star and tears into space, would appear blue-white, a searing brightness unlike the red glow Betelgeuse has worn for all of human history. That first light would come from the shockwave itself, superheated gas expanding outward, faster than anything except the neutrinos racing ahead in the dark. Then, as the fireball cooled and the ejected layers spread, the light would settle into a sustained yellow-white, the color of peak luminosity, the star pouring out as much light in a single day as our sun will emit over its entire lifetime. Over the following months, the supernova would redden. The outer layers, still glowing but cooling, would shift through orange and back toward red, a slow dimming visible week by week to anyone watching the winter sky. After roughly a year, Betelgeuse would fade below naked eye visibility in daylight. After another year, perhaps 2, it would slip below the threshold of visibility at night, no longer a beacon but a fading ember, still bright enough for binoculars, then only for telescopes, then only for the most sensitive instruments humanity can build. What would remain, embedded in the wreckage, would most likely be a neutron star. The models for Betelgeuse's mass, somewhere between 16 and 19 times the mass of the Sun, favor this outcome. A core collapse supernova compresses the innermost region of the star into an object the size of a city, a sphere perhaps 20 kilometers across, where a teaspoon of matter would weigh as much as a mountain. That neutron star would spin, possibly hundreds of times per second in its first moments, a lighthouse beam of radiation sweeping across the galaxy. Whether we would see that beam, whether it would point toward Earth, is a question no model can answer in advance. There is a smaller chance, depending on details of the explosion that no simulation has yet resolved, that the core would collapse not into a neutron star, but into a black hole. The boundary is narrow, sensitive to how much mass falls back onto the core in the seconds after the initial bounce. Betelgeuse sits near the edge of that boundary. The remnant it leaves behind will be one or the other, and we will not know which until the light reaches us. Around that remnant, whether neutron star or black hole, an expanding nebula would grow. The outer layers of Betelgeuse, enriched with oxygen and silicon and iron forged in the final years of fusion, would spread outward at thousands of kilometers per second, a shell of glowing gas colliding with the slower wind the star had been shedding for millennia. That nebula would be faint at first, lost in the glare of the supernova itself, but over the following decades it would emerge, a cloud of light growing year by year, eventually spanning minutes of arc across the sky, visible through backyard telescopes as a ghostly ring or bubble, something like the Crab Nebula, that still glows today from a supernova Chinese astronomers recorded in the year 1054. The Crab Nebula, nearly 1,000 years old now, still expands, still shines, powered by the pulsar at its heart. Betelgeuse's remnant would do the same. Thousands of years from now, the nebula would still be there, a monument in Orion, visible to whatever eyes look up from Earth or from worlds we have not yet imagined. But all of that lies in a future we cannot time. The supernova will not arrive on a schedule we can mark on calendars. It will come when the core exhausts its final fuel, when the last fusion reactions sputter out and gravity, patient and inexorable, claims what it has always been owed. That moment could be tens of thousands of years away, as the dominant models suggest, or it could be centuries, as a smaller number of analyses argue. The star does not know we are watching. What we do know is this: when it happens, it will be visible. Not a rumor in a data stream, not a faint smudge requiring a telescope the size of a building. A naked eye event, a star bright enough to read by, bright enough to see at noon, bright enough that no one on the daylit side of Earth could miss it. The last time a supernova that bright appeared in our sky was 1604, when Johannes Kepler recorded a new star in Ophiuchus that blazed for months and then faded. The last time a supernova was visible to the naked eye at all was 1987, in the Large Magellanic Cloud, visible only from the southern hemisphere, and only barely, a star that required dark skies and careful looking. Betelgeuse will require neither. It will be unavoidable. For months the sky will carry a light that was not there before, a star that died when our ancestors were still learning to speak, its light crossing the void at the speed of all light, patient and unstoppable, arriving at last to a world that had been watching the star for thousands of years and never knew what it was capable of. The neutrinos will arrive first, hours before the light, passing through the Earth as if it were not there, a ghost flood detectable only by instruments buried deep underground. Those detectors will record the burst, and within minutes the alert will go out: a core has collapsed somewhere. Then the light will follow, and the sky will change. You will not need to be told. You will step outside and see it, a star, where a star should not be that bright. And you will know, as every human who sees it will know, that you are watching something that has not happened in living memory. The explosion will not threaten you. Betelgeuse lies far beyond the threshold, where a supernova's radiation could strip atmospheres or harm life. It is far enough to be safe, close enough to be spectacular. The light will wash over the Earth, harmless and brilliant, a signal sent across centuries of space. And when the light fades, when Betelgeuse slips back below the horizon of unaided sight, the nebula will remain, expanding, glowing, a cloud of everything the star once was, drifting outward into the space between the stars, seeding the galaxy with the elements that will, in time, collapse into new stars, new worlds, new chances for eyes to open and look up. The honest answer is that we do not know when Betelgeuse will explode, and that uncertainty is itself a frontier of science. The Great Dimming was not a countdown. It was not a warning bell. It was a surface event, dramatic and unprecedented, but not a sign of imminent collapse. The question of when the star will end is a different question entirely, and it turns on something we cannot see. What is burning in the core, hidden beneath nearly 900 solar radii of roiling gas? The dominant consensus among astronomers is that Betelgeuse is burning helium in its core. Helium fusion is the second major phase of a massive star's life, the long plateau after hydrogen exhaustion, and it lasts far longer than the final stages that follow. If Betelgeuse is fusing helium into carbon and oxygen deep in its center, then the star has tens of thousands of years ahead of it, perhaps as many as 100,000 years. The number comes not from guesswork, but from models of stellar structure, from the observed luminosity and temperature, from the radius measured by instruments like SPHERE, and from the physics of how a star this massive burns its fuel. The star's outer layers may churn and eject mass, its surface may dim and brighten, but the core, if it is burning helium, remains stable. The collapse will come, but not soon. Not in any human timescale. This view is held by most of the researchers who have studied Betelgeuse closely. It fits the measured radius from Joyce and colleagues, the distance of roughly 550 light-years, the effective temperature near 3600 Kelvin, and the observed pulsation behavior. If you accept those measurements, the star is in helium burning, and the explosion lies in the deep future. But there is a minority view, and it cannot be dismissed lightly. A team led by SIO published an analysis in 2023 that approached the problem from a different angle. They modeled Betelgeuse's long pulsation period, the roughly 2100-day cycle that had puzzled observers for decades. They treated that cycle as the fundamental radial mode, the deepest breathing of the star, and asked what kind of core would produce such a period. Their answer required Betelgeuse to be larger than Joyce's measurements suggest, perhaps 1300 times the radius of the Sun. And if the star is that large, and if the long period reflects the fundamental mode, then the models point to a core already burning carbon. Carbon burning is the penultimate stage before collapse. It lasts not tens of thousands of years but centuries. Perhaps a few decades. The explosion, in this scenario, could come within the span of a human lifetime, perhaps within 300 years. Perhaps sooner. The two views rest on different assumptions about the star's size and which pulsation mode we are observing. The minority view requires Betelgeuse to be considerably larger than the best current measurements indicate. Most astronomers consider this scenario unlikely given the radius and distance that fit the observational data most cleanly. But the scenario is not impossible. The star's radius is debated, the distance is debated, the pulsation modes are not fully understood. And so the minority view remains live, a plausible path through the thicket of uncertainty. The difficulty is that we cannot directly observe what is burning in the core. A helium-burning Betelgeuse and a carbon-burning Betelgeuse can look nearly identical from the outside. The energy output, the surface temperature, the color, the brightness, all of these can be similar. The difference lies in the interior, in a region smaller than the Earth buried beneath a volume that could swallow Jupiter's orbit. No telescope can pierce that veil. No instrument can sample the core. We infer what is happening inside by matching observations to models, and when the observations themselves are uncertain, when the radius and the distance and the pulsation periods are all debated, the models diverge. The debate hinges on which pulsation period is the fundamental mode, and what radius that implies. Change one assumption, and the timeline shifts by 5 orders of magnitude. The honest frame is this: we do not know the star's exact timetable, and that uncertainty is itself a frontier. It is not a failure of science. It is the condition of studying an object 500 light-years away. An object so large that its surface convects in cells the size of the inner solar system. An object whose pulsations span years, and whose atmosphere extends beyond the orbit of Mars. The star does not offer us easy answers. It offers us data, and the data admit more than one interpretation. What we do know is that the Great Dimming was not a pre-supernova signal. Surface mass ejections of the kind Betelgeuse underwent are a normal feature of red supergiant mass loss. They are dramatic, they are rare to witness, but they are not harbingers of collapse. The star ejects mass continuously through its stellar wind. It sheds the equivalent of Earth's mass roughly every few hundred years. Occasionally, a convective plume rises with enough energy to blast a larger mass outward all at once, a continent-sized eruption that cools into dust and briefly veils part of the star. This is what happened in late 2019. The event was unprecedented in human observation, but it was not unprecedented in the life of a red supergiant. Stars like Betelgeuse lose mass this way. They shed their outer layers over millions of years, enriching the space around them with the elements forged in their cores. The dimming was a glimpse of that process in action, not a sign that the core was failing. The core debate is separate. It is quieter. It does not produce a spectacle that dims the winter sky. It unfolds in the realm of models and pulsation frequencies and assumptions about convection and mixing. It is a question that will not be settled by a single observation. It may not be settled until the star explodes, and the explosion itself reveals what was burning in the final moments. Or it may be settled by better measurements of the radius, by interferometry that resolves the star's disk with higher precision, by a clearer understanding of which pulsation modes dominate and why. The work continues. The observations accumulate. The models refine. Meanwhile, the star burns. If it is fusing helium, it will continue for 100,000 years, give or take. If it is fusing carbon, it may explode within centuries. Either way, it will not explode tonight. It will not explode this year. The dimming of 2020 was not a countdown. It was a surface event, a mass ejection, a veil of dust that has since dispersed. The star returned to its normal brightness by April of that year. It continued to pulse. It continued to shine in the shoulder of Orion, red and vast and unbothered by the attention it had drawn. The uncertainty is not a reason for alarm, it is a reminder of scale. Even the shorter estimate, the minority view that places the explosion within centuries, is a timescale far beyond individual human lives. The longer estimate stretches into deep time, into a future where the constellations themselves will have drifted, where Orion may no longer resemble a hunter, where Betelgeuse's light will still be crossing the gulf between stars. The star has been burning for less than 10 million years. It will burn for tens of thousands more at minimum. We do not know. The core keeps its secrets. What we learned from the Great Dimming was not about the star's death, it was about the star's life. We learned that a red supergiant can eject enough mass in a single event to veil a quarter of its own face. We learned that the surface of such a star is not static, not smooth, not predictable. We learned that convection and mass loss and dust formation can conspire to produce changes visible across interstellar distances on a timescale of weeks. We learned that the star is more dynamic, more violent, more alive than the models had suggested. And we learned all of this not because the star was dying, but because it was behaving. The dimming was not an ending, it was a process. A star showing us what it does. The question of when it will explode remains open. The core burns in silence. The models diverge. The observations refine. And the star continues, a point of red light in the winter sky, unchanged by what we have learned, indifferent to the debate. It will explode when its core runs out of fuel, when the radiation pressure that holds it up against gravity finally fails, when the iron core collapses in a fraction of a second and rebounds in a shockwave that tears the star apart. That moment will come. But it has not come yet, and the dimming of 2020 was not a sign that it was near. It was a sign that we were watching closely enough to see something new. You can rest in that. The star is not on a countdown. The core is stable, whether it burns helium or carbon. The timeline is uncertain, but the uncertainty is measured in millennia, not months. The Great Dimming was a surface event, a veil of dust, a glimpse of how a giant star sheds its mass. It was not a warning. It was a revelation. And the star, having revealed itself, continues. It will burn through the night, Through the winter, through the centuries ahead, a red shoulder in the hunter's constellation, vast and distant and patient. The explosion will come in its own time. Until then, the star simply is. And then, in late 2024, astronomers began to wonder if Betelgeuse had been keeping one more secret all along. Two independent teams, working from different data and different models, both arrived at the same conclusion. Something else was there. Not a star spot. Not a dust cloud drifting in the void. A companion. A second star, hidden inside the giant's outer atmosphere, orbiting through the haze of gas that spills from Betelgeuse like breath on a winter morning. Jared Goldberg, working at the Flatiron Institute alongside Meredith Joyce and Laszlo Molnar, predicted a body larger than our Sun, circling Betelgeuse at a distance roughly 2.5 times the giant's own radius. Colin McLeod at Harvard predicted a smaller star in a similar orbit. Neither team had seen it. They had inferred it, the way Neptune was inferred before it was observed, by the way Betelgeuse moved and pulsed and dimmed. In December of that year, the Gemini North Telescope on Mauna Kea turned its allopeak instrument toward Betelgeuse. The technique is called speckle imaging. It stitches together thousands of ultra-short exposures, each frozen before the atmosphere can blur the light, and builds a composite sharper than any single frame. The astronomers chose that month deliberately. Their models predicted the companion would be at its greatest angular separation, the farthest it would appear from Betelgeuse in its slow orbit, the moment when detection would be easiest. The image came back, a faint point of light, distinct from the giant, separated by a sliver of darkness wide enough to resolve. Tentative, probable, not certain. The detection carried a confidence level just shy of what astronomers call definitive, a statistical whisper rather than a shout. But it was there, exactly where the models said it should be. The paper appeared in July 2025, published in the astrophysical journal Letters under the lead authorship of Steve Howell. The authors called it a probable companion. They proposed a name, informal for now, pending confirmation. Siwarha. The word means her bracelet in Arabic, a reference to the same linguistic root that gave us Betelgeuse itself, the hand of the giant. The companion is an ornament worn by the red supergiant, circling it like a jewel on a thread. If confirmed, Siwarha appears to be a young star, somewhere between 1.4 and 2 times the mass of the Sun, not a twin. Not even a sibling of comparable size. Betelgeuse outweighs it by a factor of nearly 10. But it is no ember, no dying cinder. It is a star in its own right, burning hydrogen in its core, shining with the steady light of a main-sequence sun. And it orbits inside Betelgeuse, not beside it, the way binary stars are often imagined, 2 points of light separated by the cold gulf of space. Siwarha moves through the outer envelope of the red supergiant itself, through the tenuous gas that extends outward from Betelgeuse's photosphere like a vast invisible crown. The companion's orbit lies at roughly 4 times the distance between Earth and the Sun, a span that would fit comfortably inside the inner solar system. But measured from Betelgeuse's center, that distance is only about 1,850 solar radii. A region still bathed in the giant's extended atmosphere. The orbital period is 2,170 days. Just under 6 years. One slow waltz around the red supergiant, through layers of gas so thin they would count as vacuum in any terrestrial laboratory, yet dense enough to glow faintly in infrared, dense enough to condense into dust when conditions align. And that period matched something astronomers had been puzzling over for decades. Betelgeuse brightens and dims on 2 cycles. The shorter one, roughly 400 days, is thought to be a pulsation, the star swelling and contracting like a slow heartbeat. But the longer cycle, the one that takes about 6 years, had no clear explanation. It was called the long secondary period, a pattern without a cause, a rhythm in the data that refused to fit the models. Until Siwaha. The leading explanation now is that the companion, as it orbits, clears a path through the dust that surrounds Betelgeuse. Light blocking grains, the same kind that veiled the southern hemisphere during the Great Dimming, drifting clouds around the giant, scattered by stellar winds and convective upheavals. When Siwaha passes through our line of sight, it sweeps aside some of that dust, and Betelgeuse brightens. When the companion moves behind the giant, the dust settles back, and the star dims. Not because Betelgeuse itself is changing, but because the veil between us and the giant is shifting, tugged by the gravity of a smaller star we could not see. It is an elegant solution. It fits the data. It explains the 6-year cycle without invoking new physics or exotic processes. But it rests on a foundation still under construction. The companion is probable, not confirmed. The image is real, but it is faint, and the confidence level is not yet high enough to close the case. Full confirmation requires one more observation. The companion must be seen to disappear behind Betelgeuse and then re-emerge on the other side, proving that it is not a foreground star, not a background object, not an artifact of the imaging process. The next opportunity falls in late 2027, when the orbit brings Siwaha back around to the far side of the giant. Astronomers will watch. Telescopes will be scheduled. The question will be settled one way or another. If the companion is real, if Siwaha is confirmed, then the story of Betelgeuse gains another chapter, one written not in the star's own convulsions but in the quiet mechanics of orbital motion. A smaller star, bound to a giant, circling through an atmosphere that extends farther than the orbit itself. The two bodies are not colliding. They are not tearing each other apart. But they are not stable either. The models predict orbital decay. Slowly, over thousands of years, Siwaha will spiral inward. The drag of the giant's outer envelope, thin as it is, will sap energy from the companion's motion. The orbit will tighten. The period will shorten. And in roughly 10,000 years, the two stars will merge. When that happens, Betelgeuse will spin up. The angular momentum of the companion, absorbed into the giant's bulk, will set the red supergiant rotating faster than it does now. That spin will alter the structure of the core, the distribution of heat, the geometry of the collapse when it finally comes. The supernova that follows will be different. Shaped by the merger, a blast wave twisted by rotation, perhaps asymmetric, perhaps more energetic in certain directions than others. But that is 10 millennia away. Deep time, measured on a scale where human civilizations rise and fall like breaths. For now, if Siwaha is real, it is simply there. A companion, a smaller sun, orbiting through the haze of a giant, clearing dust as it goes, marking time in a cycle we have watched without understanding for as long as we have kept careful records of the winter sky. The Great Dimming showed us a star ejecting its own face, veiling itself in dust born from its own flesh. The companion discovery, if confirmed, shows us something quieter. A star that is not alone, a giant attended by a smaller light, the two bound together in a slow descent toward union. A dance that will end long after the last person who reads about it has turned to dust themselves. And until 2027, when the telescopes turn again toward Orion, we wait. The data is gathered, the models are built, the prediction is made. The universe will answer in its own time, and we will listen. We arrive now at the question that matters most to a living planet watching a giant star flicker in the winter sky. How far away is safe? How close is too close? And where, along that spectrum, does Betelgeuse rest? The threshold is known. A supernova must occur within roughly 160 light-years of Earth for its high-energy radiation to pose a meaningful threat to life. At that distance, the burst of gamma rays and cosmic particles could strip portions of the ozone layer, expose the surface to ultraviolet light, and disrupt the chemistry of the upper atmosphere. It would be a wound, not an ending, but a wound nonetheless. 160 light-years, that is the line. Betelgeuse lies somewhere between 500 and 700 light-years away, depending on which measurement you trust. The distance is debated, the parallax uncertain, the star itself so large and so variable that pinning it to a single number remains difficult. But even the closest estimate places it roughly 4 times beyond the danger radius. The explosion, when it comes, will flood the Earth with light. It will not flood us with danger. There will be effects. Minor ones. Real but not dangerous. Nocturnal animals that navigate by the patterns of moonlight may find themselves briefly confused by a new bright point in the sky, one that casts shadows where shadows did not fall before. Optical astronomers will face months of interference, their instruments overwhelmed by an unresolved brilliant source sitting in the constellation Orion, drowning out fainter objects nearby. Observatories will schedule around it, some will turn toward it, others will wait, and in the seconds before the light reaches us, the neutrinos will arrive. They travel at nearly the speed of light, unimpeded by the outer layers of the collapsing star. The neutrino burst will announce the supernova hours before the light does, a whisper from the core of a star in its final convulsion. Detectors buried deep in mines and beneath mountains will register a spike. A flood. We saw this once before, in 1987, when a blue supergiant in the Large Magellanic Cloud collapsed and sent its neutrinos racing across 170,000 light-years of intergalactic void. Kamiokande in Japan and IMB in Ohio both recorded the pulse. 11 neutrinos in one detector, 8 in another. Enough to confirm that the models were right, that the core had collapsed, that a neutron star or black hole had been born in the dark. When Betelgeuse goes, the neutrino observatories of the world will light up again. They will send alerts. Astronomers will turn their telescopes toward Orion. And then, hours later, the light will arrive. The last supernova visible to the naked eye within our own galaxy was Kepler's star, which flared in 1604. It appeared in the constellation Ophiuchus, bright enough to be seen in daylight for weeks, and then it faded. No one alive today has seen a galactic supernova. The last naked-eye supernova of any kind was that blue giant in the Large Magellanic Cloud, briefly visible from the southern hemisphere. It has been decades. It has been centuries, if you count only the Milky Way. An entire span of human history has unfolded under skies when no star has exploded close enough to notice. Betelgeuse will end that silence. It will not end it with violence, it will end it with light. A point source, brilliant and unwavering, concentrated into a single sharp dot rather than spread across a disk. Models suggest it will shine roughly as bright as the half-moon, sustained not for a night but for months. It will cast shadows at night. It will be visible in daylight. You will be able to step outside in the middle of the afternoon, look toward Orion, and see a star that has no right to be there, a white point burning against the blue. It will not harm you. It will not strip the air or irradiate the surface. It will simply shine. For weeks in daylight. For months at night. And then, over the course of a year or two, it will fade, reddening as it cools, dimming as the expanding shell of gas disperses. Eventually it will slip below naked eye visibility. Telescopes will follow it for years, decades, centuries. The nebula will glow, lit from within by the decay of radioactive isotopes forged in the explosion. It will become another Crab Nebula, another luminous scar in the sky where a star used to be. But you, standing on the surface of the Earth, will be safe. The distance is enough. The void between here and there is wide enough to swallow the danger and leave only the spectacle. This is the gift of distance. This is the mercy of scale. The universe is large enough that even its most violent events can be watched without fear, if you are far enough away. Betelgeuse sits in that sweet zone, close enough to fill our instruments with data, far enough to pose no threat, close enough to be resolved, to be imaged, to show us its face, far enough that when it tears itself apart, we will have front row seats to a show that has not been staged in living memory. No generation now alive has seen a star explode. No generation in 400 years has watched a supernova bloom inside our own galaxy. If Betelgeuse in our lifetime, or in the lifetimes of those who come after us, it will be a gift. A once-in-civilization event. A light that reaches across the dark and says, "This is what a star looks like when it dies." And we will watch, we will measure. We will record the light curve, the spectrum, the neutrino pulse, the evolution of the remnant. We will learn things no textbook currently contains. And we will do so in perfect safety, standing on a world that orbits a stable yellow star, far enough from the red giant that its death will never be ours. The threshold is 160 light-years. Betelgeuse is 500, or 600, or 700. The numbers are uncertain. The safety is not. You can rest here. You can close your eyes and know that the light, when it comes, will be only light. The star will blaze, the sky will change, and the earth will turn beneath it, unharmed, as it has turned beneath every star that has ever lived and died in the long history of the galaxy. The distance is enough. The void is wide, and the show, when it begins, will be ours to witness. You are watching a star change its face in real time, and you did not know that was possible until it happened. The images arrived in early 2020. 2 frames, side by side. On the left, Betelgeuse as it appeared in January 2019. A mottled sphere, bright and uneven, the surface churning with convection cells the size of planetary orbits. On the right, the same star in December 2019. The southern half had gone dark. Not dimmed. Dark. An order of magnitude fainter than it had been 11 months earlier. As if someone had drawn a curtain across half the star's face and left it there. These were not artists' renderings. They were direct optical images of a star's photosphere, captured by the SPHERE instrument on the European Southern Observatory's Very Large Telescope in Chile. Betelgeuse is large enough in the sky, roughly 42 milliarc-seconds across, to be spatially resolved by the best ground-based telescopes. It is one of only a handful of stars where this is even possible. And in the winter of 2019 and 2020, it became the only star beyond our Sun whose surface has ever been imaged changing on a timescale of weeks. The astronomer Miguel Montage, lead author of the study published in Nature, said it plainly. For once, we were seeing the appearance of a star changing in real time on a scale of weeks. No one had watched this before. The textbooks described red supergiants as variable, yes, but variability had always been a graph, a brightness curve plotted over months or years. This was different. This was watching the star's geography shift. Betelgeuse had been dimming since October 2019, fading from its typical brightness to roughly 1/3 of that by mid-February 2020. The drop was visible to the naked eye if you knew where to look, and had watched the winter sky long enough to hold the star's usual glow in memory. Careful observers noticed. The astronomical community noticed. And then the images arrived, and the dimming had a shape. 3 explanations competed in the literature, each fitting parts of the data. A massive star spot covering the southern hemisphere. A drop in the star's effective temperature, driven by pulsation. Or a cloud of dust, ejected by the star itself, drifting into our line of sight and blocking the light like smoke across a lantern. Scientists tested each hypothesis in public. Spectrophotometry taken on the 15th of February 2020 measured Betelgeuse's effective temperature at 3600 degrees Kelvin, plus or minus 25. Only slightly cooler than pre-dimming measurements, the temperature drop alone was insufficient to explain a 3-fold optical dimming. The data pointed to episodic mass loss and circumstellar dust, and the models began to converge. Andrea Dupree and her team, working with ultraviolet spectroscopy from the Hubble Space Telescope, identified outward-moving material in chromospheric emission lines, specifically magnesium ionized once. The signal was clear: gas was leaving the star. Not in the steady trickle of a normal stellar wind, but in a pulse, a surge. Material driven upward from the photosphere, through the extended atmosphere, and out into the surrounding space. A global network of observatories mobilized. Sphere and gravity on the Very Large Telescope, Hubble in ultraviolet, ALMA in the sub-millimeter, tracing cold dust and molecular gas. The Stellar Robotic Telescope measuring radial velocities. Each instrument added a layer. Each dataset constrained the models. This was not panic. This was attention. The kind that comes when the universe offers something it has never shown before. The consensus account emerged slowly, confirmed by multi-instrument, multi-year follow-up. Betelgeuse had undergone what is now called a surface mass ejection, a phenomenon previously not observed in a normal, non-explosive star. A photospheric shock propagated outward from January through March of 2019, driven by convection or pulsation deep in the star's interior. Enhanced outward mass flow followed. Material traveled through the extended atmosphere over the next 11 months, cooling as it rose. In late 2019, the ejected gas cloud cooled enough to condense into dust grains, specifically in the southern hemisphere. That dust cloud obscured roughly 25 to 50% of the star's visible southern hemisphere from our line of sight. By April 2020, the star returned to normal brightness as the dust dispersed or moved away. The ejected mass could represent a significant fraction of Betelgeuse's entire annual stellar wind mass loss rate. Estimates range from 3% to 128% of the annual rate depending on assumptions. The uncertainty is wide, but the scale is clear. This was an eruption on the star's surface, as if a continent-sized mass of superheated gas blasted upward, cooled into soot, and briefly veiled a quarter of the star. The aftermath was equally strange. Following the surface mass ejection, Betelgeuse's 400-day pulsation disappeared for more than 2 years, replaced by an unusual shorter photometric oscillation. The chromosphere was left with reduced density, as if the star had been stunned by its own violence. Infrared observations confirmed that the star's total energy output had not changed significantly over the 50 years before the dimming. The event was an extinction effect, an obscuration, not a fundamental change in the star's power. Betelgeuse had not faltered, it had simply covered its own light. And yet, for all the strangeness, this was not a sign of imminent explosion. Surface mass ejections of the kind observed are a normal, if dramatic feature, of red supergiant mass loss. They are part of how these stars shed their outer layers over the final 100,000 years of life. The Great Dimming was not a death rattle, it was weather. Violent, yes. Unprecedented in observation, certainly. But not a countdown. The honest answer is, we do not know Betelgeuse's exact timetable, and that uncertainty is itself a frontier of science. The dominant consensus holds that Betelgeuse is burning helium in its core, placing it tens of thousands to roughly 100,000 years from explosion. This estimate comes primarily from the helium-burning condition and from measurements of the star's radius, roughly 700 to 900 times the radius of the Sun, and its distance, somewhere between roughly 500 and 700 light-years away, close enough to stage a spectacular show, too far to threaten us. A minority analysis published in 2023 and requiring Betelgeuse to be considerably larger than the current best-fit measurements suggest, argues the explosion could come within centuries. Most astronomers consider this scenario unlikely given the radius and distance constraints, but the debate is live. We cannot directly observe what is burning in Betelgeuse's core. A helium-burning and a carbon-burning Betelgeuse can look nearly identical from the outside. As one astronomer put it, if it were easy to tell whether a star is undergoing helium versus carbon burning simply by observation, we could stop arguing. The star itself is enormous, a red supergiant of spectral type M1 to M2, one of the largest and most luminous stars close enough for us to study in detail. Placed at the center of our solar system, its surface would engulf the inner planets out to roughly Jupiter's orbit, or perhaps farther. It radiates tens of thousands to over 100,000 times the Sun's luminosity, though only about 13% of that energy is emitted as visible light. Most is infrared, heat bleeding into space from a surface cooled by its own vastness. It is a young star, less than 10 million years old, born with 16.5 to 19 times the mass of the Sun. Massive stars like Betelgeuse evolve very quickly, and their lives are measured in millions of years rather than billions. When Betelgeuse's core finally collapses, it will produce a core collapse supernova. Models suggest the initial flash will be blue-white as the shockwave breaks out of the stellar surface. It will then settle to a bright sustained yellow-white at peak, finally fading and reddening over months to years. Peak brightness from Earth, according to modeling by Jared Goldberg and colleagues, is predicted to reach approximately the brightness of the half-moon, sustained for more than 3 months. The supernova light would be concentrated into a single point, not spread as a disk. It would cast sharp shadows at night and be visible in daylight for weeks to months. Visible to the naked eye in the night sky for another 1 to 2 years after that. After the supernova, the remnant will most likely be a neutron star, embedded in an expanding nebula visible for thousands of years, like the Crab Nebula, a monument in the winter sky where Orion's shoulder used to be. A supernova must occur within roughly 160 light-years of Earth for its high-energy radiation to pose a threat to life. Betelgeuse's distance places it approximately 4 times beyond that danger radius. Life on Earth will be unharmed. Nocturnal animals that navigate by moonlight may be briefly confused by the extra light source. Optical astronomy will face months of interference from a bright, unresolved point in Orion. The global neutrino flux will spike in the seconds before the optical brightening reaches Earth, a neutrino burst arriving hours before the light from inside the collapsing core. These are minor effects, real but not dangerous. The last galactic naked-eye supernova was Kepler's supernova in 1604. The last naked-eye supernova of any kind was SN 1987A in the Large Magellanic Cloud, 170,000 light-years away, briefly visible in the southern hemisphere. If Betelgeuse explodes in our lifetime, it will be the astronomical event of the millennium. If it does not, it will continue to burn quietly in the winter sky, as it has for millions of years, and will for tens of thousands more. The Great Dimming was not panic. It was attention. Scientists mobilized not because the star was dying, but because it was behaving in a way no human had ever observed. Betelgeuse became the first star, beyond our Sun, whose surface was ever imaged changing in real time. In 2020, astronomers watched a star eject a mass of gas, cool it into dust, and pull a veil across its own face. No textbook predicted it. No simulation had modeled it. It was new. By April 2020, the veil dispersed, and Betelgeuse returned to its normal range. The star continued. A giant, burning quietly in the winter sky, unchanged by what humans had just learned about it. In April 2023, Betelgeuse reached a peak brightness of visual magnitude 0.0, its brightest in recorded history, suggesting the 400-day pulsation cycle re-entrained after the post-ejection disruption. You can rest inside that scale. The star revealed something new about itself, was witnessed, and continues. We've come to the end of the watch. Betelgeuse still burns in the shoulder of Orion, unchanged by what we learned about it, indifferent to the cameras that caught it veiling its own face. The dust has long since dispersed. The companion, if it is there, orbits silently in the giant's outer atmosphere, unseen except for one fleeting moment when a telescope caught what might have been its light. You stayed awake, or you fell asleep somewhere along the way. Either is fine. The dark will still be here. So will I. Wherever you are tonight, under city glow or open sky, the stars above you are doing what they have always done. Burning, pulsing, ejecting their atmospheres into space, veiling and unveiling themselves on timescales we are only beginning to witness. If you'd like to return tomorrow night, I'll be here. Safe travels.